Welcome, everybody. Thanks for joining. What I intend to do is to give a brief overview of the history of AI as it pertains to radiology, and also go through some of the vernacular and some of the algorithms, because unless you have a little bit of understanding of how AI works, it's a little bit like the Wild West. I think it's very important that as doctors and clinicians, we get some idea on how it works. So on my slide, you can see the road ahead for AI and radiology is paved with promising opportunities, and I firmly believe that, and I hope to convince you of that by the end of my presentation. Now, Amara's law says we tend to overestimate the effect of technology in the short run and underestimate the effect in the long run. I think that certainly applies to AI, around which there is a lot of hype. It's not so much about what jobs we will do, but how we will do our job. Everyone will do their job differently, working with machines over the next 20 years. And in fact, say that's here and now even. And that's a quote from the economist Andrew Charlton. If you look at the interest in AI, really in the last 2 or 3 years, on the left are the amount of money spent in research, and on the right, the number of papers published, and you can see that it's increases almost exponentially. What's quite interesting, on the left-hand panel, you'll see that the number of publications by country, and Australia is sixth on the list in ranking in peer-reviewed publications, which is way above our weight in terms of population. And if you look on the right, here's the number of publications in the AI literature, and this is peer-reviewed journals. Medicine far outweighs all the other subspecialties, so there's a great interest in this area. I think it's very important we get the vernacular correct. And this slide, I tried to categorize the terms which a lot of people colloquially interchange. So the big circle is artificial intelligence, and this would apply to any technique that enables computers to mimic human intelligence. It does use logic, and a bunch of rules will engage in a bunch of decision trees. Machine learning is a subset, and this uses obtuse statistical techniques that enable machines to improve the tasks we do or we want of it. And then deep learning, which is the smallest subset, is a subset of machine learning where the program, after a certain amount of training, can start to train itself. And speech and image recognition is a good example of that. I think it's very illustrative to look at the journey of radiology, why our specialty is so amenable to this. In the late 20th century, and I was in part of this revolution, when we went from film to PACS, so suddenly we had a digital archive solution, not only to make us much more efficient and the ability to manipulate images, but it also gave us the ability to share images and health data. We then added on that functional imaging, like we can see now as PET, SPECT, MR, and CT, all can give us functional data. And then finally, we have modalities that also can give time-related data. So you can see this, the perfect marriage of all these modalities. Why would you be interested in AI? Already, it has a similar role in image segmentation, computer-aided diagnosis, predictive analytics, workflow optimization. In the era today where personalized medicine and precision medicine is the order of the day, AI will have significant impact with its ability to aggregate large data sets. But let's not kid ourselves, it's still a black box enigma, and there are a lot of complexities in infrastructure as well as ethical implications, which day by day we're still working through. But I think the single most important aspect is the ability of these algorithms to scrape, assimilate, categorize enormous data sets in real time. And here's just a cartoon to show that AI will impact all parts of the radiology process. And if you look on the right-hand side where I say pathology detection, the real magic source in the future is where our algorithm looks at something in an image, which if you look at radiology, it's just macro pathology, and will speak to the pathology record, the biochemistry record, the digital health record, and then come to some type of risk stratification. I like to think of AI in three distinct buckets. There's image acquisition. For example, they use AI algorithms to get CT images, using AI algorithms to look in case space and get AI, MRI images, etc. And this really belongs to the OEMs. It's not something we as a company would look at. The next bucket is what I call enterprise solution. These are all the non-image interpretive functions that we occur. And this could be things like referrer analytics, online booking, virtual call centers, etc. And I'm going to talk about some of those which we're actually currently undergoing in I-MED. Then the final piece is image analysis. An example is Annalise, which is a company we were a part of, which we train algorithms to look at image interpretation and findings. It's like a second expert set of eyes. So let's look at a way to categorize artificial intelligence. And there's really four categories, and I'll go through all of them. You can see them on the slide. The first one is reactive machines. So these are the most basic form, where there's no memory. It's very task specific. These machine models tend to take data and then deliver a recommended outcome. We call it superpower because of its ability to aggregate huge amounts of data. And a good example of this was Deep Blue. If you remember in the 90s, there was a computer that beat Garry Kasparov, the world champion chess player. That algorithm had no ability to look at the behavior or past moves, but all it could do in a very timely manner is look at the pieces on the chessboard and then recommend a move. Similarly, that's the way Netflix looks at your habits and it comes up with a recommendation. Then we have what's called limited memory machines. These algorithms, which are deep learning algorithms such as natural language processing, image recognition, and other types of reinforcement learning, they're called limited memory not because they don't have enough bandwidth to remember data. They have a limited ability to remember temporal data and past behavior and then put that into practice. So it can look at specific objects and situations and make a recommendation. A good example is self-driving cars. We can look at the speed, other cars, traffic lights, lines, lanes, and then come up with a recommendation. But all this is not temporal, it's not saved for the next time into the car's AI memory, unlike we humans, where we derive meaning by having incomplete data and we can learn and remember and apply that to future behavior. And then the second last category, which we don't yet have, but people are on the way to developing, is where you become self-aware. So these are theoretical types that have the potential to understand the world and how people and entities interact with each other. And human cognitive abilities far outstrip any AI model in this area, because we know how thoughts and emotion affect others, and AI algorithms don't have the ability. But this certainly is something that could come in the not too distant future. And then the final piece is what we call self-awareness, is where it goes beyond mind. It understands emotions to be aware of themselves and how they interact with other people. I can't see that in the near future. We don't even understand as doctors how the human brain is connected and works in this way. But this is something of interest to people sometime in the future. So let's talk about generative AI. This is a way of getting AI, but it's more than simple algorithms. We now enter the realm of creativity, innovation, and imagination. Now, if you look at the history in radiology, we're not unfamiliar with AI. This paper, published in 1963, attempted to code findings of X-ray and ascribe numbers to them as an AI algorithm. It failed. In 2012, ImageNet, there was a competition and an algorithm called AlexNet decreased image classification error rate, but still didn't go anywhere. There's a famous quote in 2016 where Geoffrey Hinton said it's quite obvious that we should stop training radiologists. Well, he was wrong. In the last 5 to 7 years, but in particular the last 2 to 3 years, the amount of algorithms developed have exponentially increased. And for narrow tasks, AI algorithms will surpass humans' ability. For example, to look at data very quickly, big data sets. So what is generative AI? So it's a technology we can generate diverse forms of content, such as images, text, audio. They make use of neural networks, just like our brain does, and this recognizes patterns and structures within data. There are generative AI algorithms that have been trained on billions of data sets, and most companies will take a already formulated algorithm and then optimize it to the user case they wish, and that's what most companies do. And by far the most widespread models used are called natural language models, and they talk a little bit about that later in the presentation. Transformative AI is another term. While generative AI focuses on creativity and content generation, transformative AI really refers to transforming industry or society at large. And I think we're already there. If you look at your smartphone, which has a lot of AI in the background, it really transforms people's behavior and the way we interact. So what's the great thing about this tool? You have all the public knowledge of the internet at your fingertips. So large language models that can mimic intelligence because they've been trained on vast data sets. If you look at ChatGPT-4, 10 trillion words of contents from the internet, took 25,000 NVIDIA GPUs, a huge amount of data and huge amount of computer software and hardware. And it works very well. You can just read here. It passed the United States medical exam, uniform bar examination, and it's very good at mimicking human conversation. But it can't act as a medical or legal professional because it does not give you context. So the great value of these things is to augment what we do and act as a efficiency tool. One of the concepts that's very important is a thing called prompting, and this is very important for medical applications. So when an algorithm interrogates data, it needs the quality of the data and the answers that come, it depends on being prompted and being asked the appropriate questions on the assumption that the data set that's been trained upon is of sufficient quality. And if you look over here, look at ChatGPT-4, which is the blue line. When you use this thing called I-MED prompt, which is a way of prompting line, we'll go into a little bit more on the next slide, the accuracy goes up greatly as opposed to MedPalm, which is Google's one without prompts, it doesn't quite match. And if you look in this cartoon here, without the prompts, ChatGPT-4, which is the center part, performs a very averagely, MedPalm a bit better. With prompts, however, it performs very, very well. And another concept is called retrieval augmented generation. This allows these language functions to search a database for information relative to a prompt. So this is just another cartoon to show how that might work. You ask a question, it looks at data, the prompt then goes and finesses that data and makes sure the questions are appropriate so that the response is appropriate to what you've asked of the algorithm. ChatGPT 3.5, if you asked this question a few months ago, this is the answer you get. You have a ChatGPT-4, this is only a few months different.
Well, now that I've learned how to search the internet, I guess my knowledge has no limits.
So these agents, so the era now is, we call them agents, and the performance of an algorithm is very dependent upon these agents. Here's an example where a process has been initiated and you have a whole series of agents, and this particular agent has also got a sidebar to search the internet to get data. So this breaks down complex tasks into little pieces of useful prompting, and that makes the algorithm far more accurate. So here's an example. Using agents, we want to ask how would we score for screening for lung cancer? And what this does is it scrapes the net, goes to all these databases, it tells you, and then comes up with every database and how you would score screening for lung cancer. And just to add a bit more context how fast this area is changing, the video came out. So to train a large language model, we take voice from humans and train the model, and then we try to add some synthetic data to that. So about a month ago, the video released a new synthetic data chip that's been trained on billions of data sets, and with very little input can synthetically and high quality give you voice data to train an algorithm. So we're going to give a look, just talk about some of the common terms that you may hear of generative model, AI models. There's a model called GANs, which is a generative adversarial network. This is quite common, and what it has is that a generator and discriminator algorithm, and they oppose each other to give you the best possible type of data. And this is used, for example, human-like language, augmenting training data, predictive text. Variations autoencoders, this takes text and converts it to image, and I'll show you an example of that. And the next domain is transformers. So what happens with transformers is that it takes an input sequence, gives an output sequence, but it does it in parallel. This greatly increases the efficiency of developing algorithms and helps to bypass some of the things that slow you up in looking at large neural networks. And here's just an example of VAE, where you take the picture on the left and pass it through the algorithm. You can see on the right, you can see the gaps between the teeth, you can see the eyes, and it greatly improves the quality of the image. Other notable models, DALL-E 3. This is an image creation from text description. It uses ChatGPT as a brainstorming partner. We all know about ChatGPT, which is a natural language and understanding generation, and Gemini, which is Bard, which is Google's equivalent. That ChatGPT is a superior algorithm when you're looking to generate text. Bard is probably better when you look to do research. And to give an example, if you say to Bard, so to DALL-E 2, give me an expressive oil painting of a chocolate chip cookie being dipped in a glass of milk, depicted as an explosion of flavors. It comes up with this image on the left, but within months, that image is so improved to the image on the right. So you can see these things are rapidly evolving. So what are the benefits? Diverse content generation. These models include text, images, sounds, animation, 3D models. It can automate processes. It can generate ideas. It can simulate scenarios, and that's part of, for example, very useful in interventional radiology, and it gives you fast prototyping. So these things on this page are already something we use. With computer-aided diagnosis, you have algorithms that will look at images, look at the volume, look at change over time, even look at some of the functional aspects. Decision support systems can give you real-time updates to algorithms used for diagnosing and pathways. Predictive analytics, which we now use for referral analytics. We can now use some of the analytics to predict a referral will change their habit in referral patterns even before they have decided to change. And of course, there's this thing called opportunistic screening. So when you get an X-ray to ask a certain question, sometimes there's other data on that X-ray that's unrelated that is significant. And you see that, for example, in coronary artery calcification in chest imaging, even in mammography now, looking at artery calcification is related to coronary artery disease, coronary central detecting osteoporosis, and there's a whole bunch of these things out there. And the algorithms, because they search for a lot of areas in the image, can come up with what we call opportunistic screening. And yes, some of these applications, particularly in big radiology practice, in fact, in big medical practice, can be useful. So in personalized medicine, which also relates to remote patient monitoring, everybody's got these AI devices and wearable devices which are getting better, ability to aggregate and look at data, to look at telemedicine, to look at security. We all have security, both particularly now with patient privacy and data, and again, predictive analytics to anticipate behavior and health risks before they become a problem. It does have limits. So although it can produce compelling content, it doesn't have human judgment. And sometimes it will produce a false outcome, and we call that a hallucination, where it inserts data that is either incorrect or not asked for. And that also depends on how well the algorithm's been trained, rubbish in, rubbish out. So these models are based on huge data sets, and we've got to make sure the quality of the data set is appropriate. And there are many ways, and I won't go into them because we're running out of time, but there are many ways to make sure the algorithm reduces the potential hallucination. And you have just some of these things down the bottom, which are called prompt engineering, etc. Now, we can use these algorithms to educate, both at medical school and in registrar training, in fact, even with post-training people. So adaptive learning, these can analyze a person's performance and learning patterns and make sure that you can optimize training to the way that patient learns or that student learns. You know, virtual mentors, these are intelligent chatbots and virtual assistants. You can have precision assessments. These pinpoint strengths and weaknesses when you evaluate people's performance. We use it and are developing algorithms to automate documentation, intelligent scheduling. As we know in radiology practices, a lot of the scheduling based on the practice, who's there, the modality, and can act as intelligent assistants. I might skip this other to say that we're well down the line in I-MED of developing a virtual typist, and I think some of those things Sajith might cover in his presentation. But basically, these typists will type reports in an intelligent way in the style of the person reporting. And we're developing what's called a virtual call center, because the problem, if you look on the left, is you have a higher bandwidth call rate, high staff turnover, it's costly to run, etc. And if we can enhance that functionality, it's better for the patient, better for the referrer, and better for the radiologist, and improves patient outcomes. Just before I finish, I think one of the really important things is we need to prepare radiologists, in fact, doctors in general. And I think these things need to either be done at medical school or as part of your specialist training, but you have to set appropriate expectation. What challenges could benefit? Got to tailor AI to what the clinical area of interest is. Networking is social media engagement. There's a lot of information. It's an essential tool that forms part of knowledge. Got to learn longitudinally. So you have to learn over time, place and function of these things, and also to enhance interdisciplinary skills, because we never work in isolation. There are referrers, there are physicists, there are data scientists, etc. And I'm out of time, so I thank everybody and will hand over to Sajith.
Just said, thank you, Dr. Shnier and Team I-MED for inviting me today. So we've had a really great overview on the many, many kinds of AI in play today and how it's going to transform our industry. To follow on, I'm going to focus on some of the technologies that we already have in use today that can help reduce errors in radiology reporting, and why generative AI will change the game once again there. Firstly, where is our industry today? We know that radiology has seen massive advances in terms of scanning technology over the last decade, and in this decade, it is the first medical specialty to really adopt AI at scale. We know radiology adds incredible value to patient care, and this has led to significant industry growth. With this, however, there is an element of being a victim of its own success. This is to say, we now have unprecedented volumes of scans to report. These pressures have an impact on our error rates, and I'll summarize this nice ESR article, which sort of categorizes it in a logical way. Conceptually, we have professional causes of error and then non-professional causes of error in reporting. The professional causes are those that result in misdiagnosis or incorrect diagnoses. And the number one error, or error type, is perception. This is where the radiologist simply does not see the abnormality. Errors in interpretation, where the radiologist sees the abnormality but doesn't make the correct diagnosis, is less common, but the proportion is still significant. The article also touches on insufficient clinical information and inadequate review of prior examinations as a major cause of professional errors, but this is much harder to quantify. Moving to the non-professional errors, these are the human errors that we make. Fatigue, be that purely due to volume of work, working night shifts, and interruptions, are all significant contributors to all errors. In Australia, radiologists go through an intense training program where systematic approaches to both interpretation and reporting are taught. Companies like I-MED promote the concept of ongoing learning through review of errors, with statewide case review meetings, peer review systems built into our reporting workflows, and clinical auditing. It seems like we've almost maxed out what we can do in terms of upping the education of our radiologists with the time we have. So we really need advances in technology to help us bring our error rate down to the goal of 0%. In 2024, I think errors in perception in particular, and those linked to those non-professional causes we mentioned, can be greatly reduced with the help of AI assistants. One type of AI assistant in full force today at I-MED Radiology is a diagnostic assistant called Analyse AI. This assistant sits alongside our image viewers when we report and acts like a digital buddy that does a second read effectively of chest x-rays and CT brain studies. Some things are easier to miss than others in radiology, and an abnormality that is very small is always at a higher risk of being missed. These image interpretation deep learning AI systems can interpret the image in very small groups of pixels, so they're exceptionally good at picking up small things, like the tiny lung nodules you see in this little GIF image. This sort of technology is proving now to reduce mortality due to lung cancer through early detection and treatment around the world. Another factor that makes perception difficult is when the textural difference that denotes the pathology is really subtle, like this case of early acute stroke. AI systems can be trained to be incredibly good at detecting textural change that is almost invisible to the human eye. How does it do this? It's actually a process where, to create the training data, CTs are paired with other imaging modalities, like MRI in this instance, that show the pathology much more clearly. And the labeling data is made using this as a reference. Not a fair comparison, I know, but the AI is obviously here to help us, and the patient wins at the end of the day. What's more is that these AI assistants start processing cases in the background as soon as the scan is done. And then if an acute pathology like a stroke is detected, it can push that case up to the very top of the reporting worklist so radiologists can get to it quickly. For any acute pathology like stroke that is time critical, this makes a massive difference on patient outcomes. The third perceptive error I'll talk about is satisfaction of search. This is when there are simply many findings in one study, and the radiologist's attention might be drawn to the major findings, and it makes it really easy to miss something ancillary or towards the other side of the image. In this case, you can see there's hemorrhage in the right temporal region, as well as subdural hemorrhage, and the AI has showed us that there's a mastoid fracture from impact and trauma on the right side. It's easy to draw attention away from a subtle fracture closer to the occiput, and at the front of the brain, the contractile hemorrhage that's also present. Having an AI assistant that can list all of this out for you nicely whilst you're reporting is incredibly helpful if you want to produce an accurate and comprehensive report for these complex cases. Moving away from image interpretation more to the human error side when writing the report itself, current generation voice recognition systems can help us from making the more silly errors in our report that ultimately confuse referrers and patients. Like in this example, natural language processing compares the side of the region imaged in the report heading to the side stated in the body of the report. It identifies that there's a mismatch and flags that to the radiologist before they sign off the case. Another example is anatomical words which are similar being mixed up. And this can often simply be due to something like a bit of background noise or someone else speaking during the dictation of the report. Here, natural language processing can identify that this procedure is an X-ray of the hand, but the body of the report is talking about the metatarsal bone in the foot. So let's talk about generative AI. AI already had too much jargon with a lot of overlap in meanings to begin with, and generative AI adds another arm to this. I'll try and break it down into functional baskets to make it easier to understand, and have some real-world examples as well. From the left, it's important to start with traditional programming. For input X, output Y. We have simple programs like this working for us all the time, but their limitation is that they can never deal with an input they haven't been programmed for. Then in the middle, we have analytical AI, or what some people are now calling traditional AI. This is where AI models are trained using labeled data to detect a particular feature or classify something according to a criteria. And that's exactly what we saw with our diagnostic assistant and our VR error checker before. The big difference with generative AI is that the AI is generating outputs that don't have to conform to any set criteria, but rather the AI defines the ideal type, length, structure, and even tone of the output all by itself. Everything's easier to understand with examples. So a good example of traditional programming we see every day as radiologists is when VR software autofills the examination header based on a procedure code. Simple programming can easily make XR-right hand from the procedure code convert to X-ray right hand in the report examination heading. This is great if you work in a practice that has a consistent procedure code all the time. But what if you work for a teleradiology business? We have X-rays coming in from many healthcare providers with slightly different systems and procedure codes for different sites. If you use simple programming, any difference to what is coded X-ray right hand will result in an error. But if you incorporated a very simple natural language processing algorithm, you could have a system that could understand all the different ways to say X-ray and all the different ways to say right hand, and ensure that it always mapped nicely to have a report that was titled X-ray right hand. The important thing to note here is that the classification list, in this particular case would be every possible examination header, has to be predefined. Now let's compare natural language processing and analytical AI to generative AI by looking at two AI systems you've probably used already, Apple Siri and ChatGPT. In the leftmost screen, you can see that if you ask Siri about the weather, and you can ask that in many different ways, Siri can classify this internally to something like, my master wants to know the weather. And it is programmed when it gets that natural language classification to pull up its weather app. If you want to ask Siri something that requires a bit more niche knowledge, like a medical question on whether a patient should have a CTPA study with contrast whilst breastfeeding, you'll find that it struggles. The question is simply out of its scope. In the last box, you can see how ChatGPT, which I like to call real AI, handles such a question. And notice that in this prompt, as Dr. Shnier was explaining the importance of prompting, I've asked it for it to give me some references from reputable sources. Because ChatGPT can define the scope of its output and make that appropriate to the question, it can give you the response you're after. Yes, it's safe to proceed with a CTPA examination because the proportion of iodine transferred in breast milk is basically insignificant. And it'll give you links to reputable sources like RANSCA and the American College of Radiology, so you can verify that answer. So to recap, the big advantage of generative AI is that this AI system can perform a very broad scope of functions, and the functions can be tailored to what the user requests on the fly. This is incredibly useful for enterprise applications, and a broadly capable large language model like ChatGPT can be instructed quite simply to perform a massive number of tasks. As Dr. Ron explained, multiple AI agents can work together in chains, and they can even pull information from the internet or company document repositories to accurately answer questions. And the last point I'll make in saying why there's advantages of generative AI is there is a difference in the scale of development that's occurring thanks to the big tech companies. Because these companies have seen the massive potential that generative AI poses, they've invested heavily to accelerate its development. Whilst not an apples-to-apples comparison, if you look at one of the largest popular NLP models called Spacey, and then compare it to ChatGPT-4, it's not even a fair comparison because ChatGPT-4 is 2,000 to 3,000 times the size. So remember how our VR software could flag left-right errors and anatomy mismatches for us by reading our reports before we sign them off? Let's see how features like this could be used to supercharge error checking using generative AI. So I want everyone to start reading the CTPA report on the left and see how many errors they can pick. So what did ChatGPT say? It found that the radiologist didn't click the record button fast enough when they dictated the impression, and it missed the no before pulmonary embolism. This is a very common mistake, but it's always confusing for the referrer, and it ends up with a busy clinician having to make a phone call to a busy radiologist to clarify the result. It's also found a similar left-right error in the location of described lung nodule, which needs to be corrected. And most impressively, it's realized that the radiologist has made a recommendation according to the Fleischner criteria on how to follow up this lung nodule, which is really good. But the recommendation is for the wrong size category of nodules. And that would completely change how the patient would be followed up. Wouldn't it be great if every single report we had could be checked just before we signed it out with some sort of intelligent assistant like this? On a similar train of thought, the article I mentioned at the very beginning cited that insufficiency of clinical information and errors due to lack of prior studies was a significant cause of error. In defense of all radiologists, it can be generally difficult when a patient has had multiple scans in the past to read through every scan and retain every detail before reporting the new study in front of you. Large language models are the perfect tools to create summaries for us of this information, and that they can read this information so quickly that we can almost have it generated for us live as we open the case. The last concept I want to touch on is multimodal generative AI. And this is specifically generative AI models that have vision capabilities. So ChatGPT grew its eyes in late 2023, and shortly after, open source projects like Lava here emerged. And here you can see Lava being asked a question about a painting, and it's responding saying, "This is the Mona Lisa." It's giving a pretty intricate description. Being in radiology, we are very much in the business of imaging. So is there scope for a multimodal error checker to evolve to actually look at your report, check that the statements you're making are true to the image as you're doing it? For everyone that thinks that this sounds like alien technology, here's an example of a project where a research group trained one of these open source models I mentioned with radiology data. So it's asking the question, is there consolidation? No. Is there pneumothorax? No. Is there a pleural effusion? No. Is the heart normal? Yes. Is the mediastinum normal? Yes. Then finally, are there any acute fractures? It's saying, yes, you've missed a fracture. There's an undisplaced fracture, the left 7th rib and the left 8th rib. And there it is. To wrap up, what do we have to do to bring this technology into our industry? There's almost no doubt that big tech companies and research institutes will continue to advance development of generative AI faster than we can comprehend. What we need to do from the medical side is evolve efficient methods to validate the performance of these models. Our governance bodies and governments have to develop frameworks that support the safe implementation of generative AI. And in healthcare in particular, we have to develop methods to guarantee the security of patient data whilst utilizing these tools. We also have to continue to push forward with our integrations for information sharing, because ultimately this all depends on data. I think that's just about time for me. So thank you for listening. I hope that gives a bit of context on the big trends we're seeing in generative AI.
Thanks for that presentation. We do have some questions this evening. Our first question is from Michael. He's concerned that AI may lead to over-reporting. We just wanted to get your thoughts on that. So while AI may lead to fewer false negatives, is there a concern that it will also result in more false positives?
Happy to take that one. I'd like to first answer the question by society's expectation of technology. We have an expectation that technology is perfect and that humans are allowed to be imperfect. And I think that's a journey as a society we have to go on. I think well-trained algorithms, there may well be a degree of over-reporting, but remember, at the end of the day, it's up to the radiologist's responsibility to either reject or accept the features. Remember, this does not generate the ultimate report. The doctor is the person that takes responsibility for the final report. So yes, there may be some over-reporting, and it does happen. Over time, as the algorithms are trained on more data, that number will reduce. It's not perfect, but it's there as another ancillary tool to help you.
Thank you. Our next question is from Philip, who asks, how do the AI systems we're talking about and using actually integrate with our radiology software? And he's saying in GP land, so far, there's no integration at all. There's just a smart speech to text bot that they use.
Are you trying to take that one or me? Or?
Yeah, I can take it. So the answer is we have to drive that. We have to get all of our vendors to open up, I guess, APIs that allow access for things like large language models. And there are enterprise-grade large language models. If we're concerned about security, we can actually host versions of these on our own on-prem hardware. And we basically have to push forward that allowance of access to make that sort of technology be able to function.
Thank you. Another one from Philip. He's actually referencing a Billy Connolly video of him talking to a car, which has no idea what he's saying. How does AI cope with strong accents when converting speech to text?
I'll answer some of it, and Sajith can answer some of that. The answer is it should be first. It should be language agnostic. So all the popular languages already are covered by the AI algorithms. And that's just merely a training issue. So if you have an accent and hasn't trained on enough data, it may or may not recognize it. But over time, the model can be trained to not only recognize any accent, but also thoughtfully process keywords to answer a question that hasn't been asked in a manner that may solve the problem. Sad, I don't know what your view is.
I agree with that answer. Basically, if the training data has the right distribution, in this case, if we cover all accents, the model should be able to perform.
Thank you. From Stephen, radiology, lung cancer screening has been mentioned, and chest physicians are aware it may be introduced soon. It could be a massive logistical issue. How will AI help if it's a reality in Australia?
I'll take the first half. Agree completely. I think the system's going to be overwhelmed. Potentially, AI could not only categorize and find the findings, but potentially could populate the templates completely so that the reporting radiologist at the end of that process can just check for accuracy and agreement. I think that's where we're going to have to end up, because if you look at the potential stats, there's not the infrastructure to cope with what could be coming. Sajith, what your view?
Yeah, I think we're going to see a huge increase in the next, I guess, when the lung cancer screening program starts, of volumes of CTs to report. And a key part of the lung cancer screening, I guess, framework is to measure the size of nodules. So AI that can automate that process and give you a nice list of these are nodules in this lobe in a logical order, and maybe it'll have a nice widget where you can scroll through it to match it up to your PACS imaging. That would be, I think, something that would be really useful in not bogging the radiologist down by doing measurements.
Thank you. Next question. To what extent would the radiologist take full responsibility for the validation and ownership of each report? Can you see a situation where a radiologist would disown a generative report post-publication if it was linked to an adverse result?
That's a complex question. So let's just start with the report that is released is always the responsibility of the radiologist. There could come a point in time where a lot of the menial tasks, and I call them menial in a generic sense, where a lot of studies that are more simple, like fracture, etc., may be interpreted by the generative AI, and we're not yet in a place where the AI will sign off. But it can be used as a risk stratification tool and increase efficiency, but medico-legally, at this point in time, the responsibility is on the radiologist to agree, disagree, ignore, accept whatever the AI finding is.
Next question is, do you see a time when AI is used to do screening first reads to identify anomalies and exclude them from needing formal reports? And if so, when and what would be the technological, legislative, or practical hurdles in doing this?
The answer simply is yes. There is now reams of literature to show, for example, in mammography, as initial read, as a second read, AI actually improves the outcomes. The legislative piece is complicated and way beyond the remit of this conversation, but if there is a doctor inserted anywhere into that paradigm, it's their ultimate responsibility. Sajith, I don't know what your views are.
I agree where if you've got a program where there's a double read and the AI's performance is validated, there's definitely scope for AI to be that second reader. But I don't think in Australia, we're probably not in a position where, for example, normal studies are not reviewed by radiologists retrospectively. But it could be really useful to down triage those normal studies, because they're very likely to be normal, and up triage studies with abnormalities and have them ordered by radiologists first.
Just 2 comments on that. It's already being tested as a triage tool in hospitals where after hours or on weekends there is no radiologist, so as a free read. The second problem, and chest X-ray is a very good example, is to agree what is normal. So, for example, small bands or subsegmental collapse might be viewed in an inpatient as normal because they're lying in a bed by some and not by others. So I think where you place the filters is critically important and requires agreement that we're not near that yet.
We actually have someone joining us from Ghana tonight, and the question they have is, what are the implications of poor network connectivity in low-income countries on the integration of these sorts of models?
So there's 2 answers. There's no immediate answer other than if you look at SpaceX and all the low-flying satellites, to be able, we in Australia, for example, provide services to some outback communities that don't have internet, but they actually get better bandwidth than some of us in the big cities through to the low-flying satellites and SpaceX, etc. So the first answer is I think a lot's going to become, technology will solve a lot of that. The second part is there are now streaming and compression algorithms that will make that a lot more efficient. So there's no immediate answer, but there are solutions that could affect not everybody, but a good part of the world.
Great, thank you. Our last question for the evening, will AI reports start to be used an alternative to radiologists' reports in the near future by hospital radiology departments and private radiology companies?
Definitely not in private. Remember that in private in Australia, the provider number is owned by the doctor, and the doctor therefore has to take responsibility for the report. It could happen, but I personally would never do that. In the public system, I'm not sure. If you believe the media and what we get exposed to, there are thousands and thousands and thousands of unreported cases. If you had something that could at least start risk stratifying those cases, I think it would be invaluable. I don't know if it's the final decider, but I think it will certainly help with patient care and backlog.
Great, thank you. That was our last question for the evening. So thank you to our audience for joining. Thank you, Dr. Shnier and Dr. Karunasena, for your presentations. If everyone can stay online and just fill out your evaluation survey, which is found in your handouts tab, and we will see you next time.